So welcome everyone. Let's continue the discussion on deep learning. So choosing a network architecture is key in reaching your goal of trying to build a classifier or solving a regression problem. So some neural network architectures are explicitly designed to generalize well on particular types of data, like for example, convolutional neural networks. These are designed for computer vision problem, image classification, things like that. When comparing two networks with similar number of weights, the deeper network usually will give better generalization performance than the shallower but wider network. Deep learning systems perform better than any other pure machine learning approach for high-dimensional inputs like images, video, speech signals, and so on. Furthermore, deep learning models lack the compositional and quantificational expressive power, so you don't really have any explanation of how the network is able to classify the image because there's just no expressive power in there. And they also may produce unintuitive errors. So they tend to produce input-output mappings that are discontinuous sometimes. Okay, so you show two images of the same person, but slightly different, and you can get two different identifications in there, and that's because their output is not continuous. This is an example of the test set error for two networks. One of them is a 3-layer network, and the other one is an 11-layer network. And you can see how wide this network by looking at the number of weights. So we're talking 40 million, 50 million, 60 million weight. So imagine the number of neurons. Of course, when you read this, keep in mind this book is from 2021. Now, for example, when you talk about models in LLM models like Chap21 or other similar models, these are in the billion of parameters. So this much bigger models than what you've seen here. However, you can see that for the 11 layer network, in that case, the error continuously goes down. So even if we're able to increase the number of neurons more, we would probably even get lower out of sample error. This data comes from an early version of Google's system for transcribing addresses in photos taken by street view cars. So the key, of course, is not to overfit the data. So we always talk about generalization because that's our goal, is to generalize well to new data. So neural architecture serves to explore the state space of possible network architecture. So we're trying to find the best architecture for the network, not to do well on the training data, but to generalize well. So there are different approaches. We can maybe train one big network and start going down from there just to reduce the overfitting. We can maybe use some kind of hill climbing with mutation operations to again keep the size of the network under control. We can combine maybe a genetic algorithm or some other algorithm to combine together multiple networks. So there are ways to play around with the network architecture search in order to find a network that generalizes well. One way we discussed before is regularization. So regularization by enforcing some weight decay. Remember, the idea behind regularization is to add a penalty to the loss function, and that penalty is proportional to the size of your weights. So the more neurons you have and the higher the weight of these neurons, the higher the penalty. And the network, as it's learning, is going to try to reduce the weights of the neuron and get rid of some of them completely in order to reduce the penalty part of the loss function. So this is one way we can reduce overfitting and improve generalization. Another way that is very popular is called dropout. So dropout, essentially, what the idea here is almost like ensemble learning that we were talking about earlier. Essentially, in a hidden network, what you're going to do is we're going to drop out some neurons at random from the network, which essentially will force the network to be more robust, okay, and still make a prediction after missing these neurons. So we keep adding this dropout layer after each one of the hidden layers to regularize for us. So what it does is that it creates a very large ensemble of incomplete networks, essentially, because each network will be missing a bunch of neurons in each layer. And then the final output, the final prediction of the network is going to be a combination of all these incomplete networks that you trained by doing the dropout operation. So this works very well in practice, and it has the ability to definitely help your network generalize better. Now, another type of network is the RNN, or recurrent neural networks, and these allow cycles in the computation. So these are important because they allow us to deal with sequential input. So everything we talked about so far, the training record was essentially a snapshot taken at one point in time, whether it's a picture, an image, or a set of features for restaurants, whatever. It was just a snapshot. What if the input comes in over time, like a time series, for example, like a stock price or anything else that changes with time, and I still want to make a prediction after each time step? So in that case, we use a recurrent neural network. So as you can see, the input comes sequentially, x1, x2, x3 in that case, and then we still have the weights that we're optimizing, but we generate after x1, we generate an output y1, and then after x2, we're able to generate a new output y2, and so on. Typically, these outputs y1, y2 are fed into the next layer as well in that case. So the same network unrolled over 3 time steps, as you can see here, will create a feed-forward network. Okay, and you can see that the weights impact all the time steps. So this is unsupervised learning. That's not very important for us this week. So let's stop here, and I'll see you in class.